laws. She has 3 edited books in the area of image processing, geospatial analytics, and intelligent computing on her accounts. Dr. Sangeeta Chaudhary is IEEE Senior Member, IEEE GRS and IEEE WIE Member, ACM, CSI, ISRS Life Member, and IST Life Member. She is former chair of IEEE WI Affinity Group Bombay Section and former vice chair of IEEE GRSS Bombay Chapter. She is manuscript reviewer of many Indian and international journals. She has been a conference chair, session chair, and reviewer of many national and international conferences. She has organized technical workshops and activities for UG, PG students and faculties under umbrella of IEEE GRSS. She has delivered invited talks and conducted workshops in the domain of GIS, image processing, and cybersecurity. Her research interests include satellite image processing, pattern recognition, information security, advanced databases, geographic information system, data analytics, and high performance computing. We welcome you, ma'am. Please accept our token of respect and appreciation.
Yeah, thank you, Shaila madam. Um, yeah, good evening to one and all present over here. So just I would like to check whether my screen is getting shared. Yeah, I hope it is visible.
Yes, ma'am.
Okay, yeah. So yeah, I'll be just putting my video off.
Ma'am, for a few minutes, please uh, put your video on.
Okay, fine,
We
fine,
can
no
take
issue. Okay,
screenshots.
yes. Okay. This is the probably first session of this ATAL FDP, and the title which was mentioned was in HPC, but I thought as this is the FDP on advances in HPC and quantum technologies, and of course we are seeing all this through for the data driven application. So I just changed, modified it completely. Instead of HPC, I'll be talking on quantum, and that too I'll be mentioning how this quantum will be very helpful in machine learning field, and what are all different evolving and emerging possibilities we have in quantum world for this machine learning. So although this is the first talk, few of the things I am presuming that the participants are knowing, as this is the advanced FDP. Of course, I'll be touching up the few basic concept, and I'll be putting more emphasis on the machine learning and how exactly this quantum will be useful in machine learning, and what are all different kind of algorithms we can probably modify from our normal classical machine learning to quantum machine learning. So that is the overall idea about my talk, and of course I'll be giving some insight on what kind of platforms can be used in open source as well as proprietary, and what are the research trends if somebody wants to pursue their research in this particular field. So, to begin with, as in the keynote talk, Sir has given you the blend of HPC and quantum. So, possibly everyone who have joined over here have a little knowledge about quantum computing and how it is different than the classical computing. So, just to give you a simple example, like early up to this, by using the classical computers, we were using, or we were representing the bits in terms of zeros and ones. Now when we are moving from classical to quantum, the bits are now represent in terms of qubits, and not only in zero and zero, either zero or one, we are trying to represent it in combination of zeros and one by considering the this thing like the intermediate values as well as the states which we are calling over there in the quantum field. So basically we are trying to represent it with the help of qubits instead of the classical binary bit. Okay. There are so many what we can say, the theorems, and also I'm not really going into the quantum mechanics, because again this is very vast topic, and it requires 2 to 3 hours to explain the complete thing. So I'm just giving you the overview kind of thing, so that you can just get an idea that what is the difference between classical and quantum, and probably my emphasis will be on machine learning. When we say the basic quantum computation, as I mentioned you, instead of 0 or 1, we are trying to represent the bits in 1, 0, or both 1 and 0. So basically, the a state which we are trying to represent. So the famous superposition theorem is very much applicable or used over here. And whatever states we are trying to use over here, so we are having 2 raised to n minus 1 states over there, and we are trying to represent those states by this kind of representation, where this ai will be the states, and possibly we can say if we are summing up all the states, it is coming out to be one. And that is how we are trying to represent it. Those who are familiar with the signal processing and the hadamard transform or fourier transform, to understand this basic representation and working of quantum is very very easy. So now if suppose I'm trying to represent it by using 0 or 1, so I'm just trying to represent this like this, okay. And of course this 1 by root 2, this is coming from the hadamard, which I'll be telling you in the next slide. So basically I'm trying to represent like this, or maybe like this, where I can have a combination 0 0 0 1 1 0 and 1 1. So just I wanted to say that instead of just 0 or 1, we are trying to represent it with the various combinations of 0 and 1, with some kind of factor which is being used over there, and possibly it is coming from the hadamard. So just to represent this kind of states which we are having in quantum, so if you want to represent n qubits, okay, so you can have 2 raised to n by 1 matrix for representing it. So if you want to represent 0 state, so you can represent it by using the n qubits as 1 0. Then if you want to represent 1, it can be represented at 0 1. And of course here, by using the superposition, you can represent it by using 1 by root 2 and 1 by root 2. So just to show that how these things are coming up. So yeah, of course, one more thing just I want to highlight, that you can apply some kind of unitary transformations, and this will help to change the state or quantum state from one state to another state. And of course, some of the properties which are very very essential and helpful over here is the conjugate transform property, and it is very simple. So at the base, if you see the mathematics of the quantum, it is coming from physics, but if you try to understand it, and if you have a little bit exposure of few basic mathematical preliminaries, it is easy to understand this kind of mathematic. Of course, here I'm not just giving you the just like how the things are easy, but the problem is, even if you're understanding, the real crux is how you can use it, and of course what kind of hardware is being used, whether it is possible to have those things, we can we simulate the things and do, because nowadays we see that tremendous data is available, and we want to do lots many application which require intensive use of data. So in what way it should be used, that is the important. Yeah. So as I mentioned here, we are trying to use the hadamard. So before saying this, just I would like to show you a schematic, the visual representation of the this particular diagram, or the quantum bits, qubits. So you can see here, three things are very important over here in this representation. We are having one square box, which is nothing but your hadamard transform matrix. Here we are having some gates. Okay, so we are trying to use here 2 gates, and just I would like to highlight those things. So this is the simple hadamard transform. Those who are coming from the signal processing field, they might be aware of this, and we are trying to use this. And when we are multiplying this two, we are already getting this as a unitary or the unit matrix over here. So same thing we are trying to use over here, and of course we are using NOT gate and we are using C NOT gate. Okay, and when we are trying to use it, so here you can see we are using hadamard, not gate, and synod gate, and we are trying to represent the state 00 with the help of this. Okay, so these are the parameters which we have taken, or coefficients which we have taken from the hadamard, and we are trying to represent this, or we can represent like this, or we can represent like this. So the schematic is easy to understand. Okay, and basically you can understand how the quantum is working. Now I'm going from the basic thing to the application. So if you can see, we are having the one of the what we can say, the field, or we can say it's a NISQ, this thing, and that stands for it is standing for noise immediate scale quantum. And according to this, okay, what are all different applications which we can have for the by using the quantum this thing infrastructure, or maybe the quantum computing. So the very first thing is quantum simulation. So if you can see over here in quantum simulation, okay, just to save the bandwidth, I'm just switching off my this thing. Yeah, I hope it is visible. Yeah. So here, if you can see, lots of experimentation which people are doing in quantum, that will be simulation sort of experimentation, because the real quantum computer availability of that thing is very, very rare, and we know that only IBM is having that particular computer. And of course many of the premier institutions like IITs or CDAC, as sir has given you some insight, they are trying to build the indigenous platform for that, but still it is not possible to come up with the actual quantum computer. And if you see, to run the quantum instructions, or the operations, quantum operations, okay, you need to pay high to IBM. But of course there are some simulators which are made available for the academics and for the researchers, which can be used, and there probably people can do some kind of programming. Okay, so possibly here, maybe you can ask the question that whether we can do some kind of experimentation, and probably it will give me the more speed compared to the HPC. So answer is yes, we can get more speed than the HPC, and that's why you might have seen in the previous in the previous session, which was engaged by my teacher. He was showing the integration of HPC and quantum, and how they are trying to have a hybridization of both, so that possibly we probably can use. But of course here, the problem is the fidelity of the data which we are trying to use for the applications. The noise suppression, correction, all those things are very, very important, and if you are not setting those kinds of things properly, possibly the exponential speed you are expecting, that speed you won't be getting. Now coming to the second application which we are having, that is quantum machine learning. And we know that machine learning is one of the fascinating field, and people are trying to use it for handling the large data sets, and coming up with some kind of decision with the help of this quantum machine, with the help of classical machine learning. So can we have a quantum machine learning? So possibly here, the problem now, as we know that in today's this thing, we are having classical deep learning also. So here the intention is, can we run the quantum neural network that is capable to learn the patterns or the distributions, which is far better than the classical deep learning? So here the answer for this question is, possibly it may yes, or it may not, it may no also. Because if you are trying to use some kind of variation of the classical neural network, which is called as quantum neural network, okay, so possibly it can give you better result, but of course there are some kind of problems which are present over there, and that need to be addressed. So I'll be touching this topic again in the subsequent slide. Of course we know that optimization is playing very, very important role, and we want to use optimization at every step, so that we can get the accurate and speedy processing of the thing. So can we use quantum optimization? So, of course, here answer for this is also yes, but of course, here the power of energy which is being used, and we know that quantum is requiring a large power. Okay, and of course, if you have a quantum setup, okay, then there are many factors based on which kind of basic schematic you are using for quantum. Say, for example, you are using photonic, then of course you are getting better this thing and less maintenance is there. But you are, if you are using the infrastructure which is having the communication using the air communication, then possibly there are many problems existing, and those things need to be addressed. And there are few kind of initiative, or we can say the solutions which was given by one of the scientists who is pioneer in giving multiple such kind of algorithms and solutions, and that scientist is Grover. So we'll be seeing the algorithm also which is being proposed by Grover, and that is one of the very popular algorithms in the quantum field. And of course, along with this, can we have some kind of applications which is using the randomness, or maybe some sort of linear algebraic operation, or some kind of non-linear operations? So of course, here we can possibly do that, but still there is no such kind of infrastructure available readily everywhere so that people can work. But surely, if you see the quantum simulation and quantum machine learning, many people are trying, and they are trying to do the implementation of those things, because lot many simulators are available and people don't need to really invest on purchasing that costly this thing. If you take some kind of IBM platforms, you it is highly paying. For fraction of second you need to pay a huge thing. So depending on that, you need to set up and you need to see whether really you need a quantum computing to solve that problem. Okay, so basically it is the same thing which is coming from lot many years. So when machine learning came in picture, or deep learning came in picture, everywhere people started using it. But first we need to understand, do we really need to use such kind of things to solve the problem which we are having in hand? So similar aspect is applicable over here. But here up till now, or maybe in today's date, people are using quantum simulation and quantum machine learning, and still many people are trying to come up with lots of research in the quantum optimization field. Now, to understand how exactly these things are working, so for example, you want to use such kind of quantum heuristic. So that's why I just mentioned you, it is very much important to decide where to use, and whether to use it or not. Okay, so that's why here some of the questions are there, and you need to understand, if the answer for this question is yes, then only you should go for quantum. Otherwise you can use the simple classical approaches. So the first question, if you can see, do you bid some good classical methods? So answer is no. Then probably you need to you need to work more on that, and then you need to improve. If as, then again you can see, do you bid all good classical methods? Okay, then again you can see, is your performance is so much better that it would be crazy to do it without quantum computing. Okay, so likewise here, just to tell you from this slide is, first of all, you need to see that if the operations are getting performed by the normal computer or classical computer, then don't shift it to quantum. Because again, when you're shifting to quantum, the power requirement and all those things are very high. And of course, some of the applications which you want to really use that, and it is possibly can be done on the simulator, then possibly you can go and do on the simulators. So coming to the field of quantum machine learning, so typically here people are trying to use quantum machine learning, okay, for in two kinds of this thing. what you can say, verticals. So either they want to shift from the classic machine learning algorithm to quantum machine learning algorithm, or the data which they have in hand there, that is having the nature, the traditional nature of data, or the nature of the data is itself like quantum. So if you can see here, this is the quadrant which is, or this is the particular categorization which is very very essential to understand. So we are having four quadrants over here: CC, CQ, QC, and QQ. So you can possibly see this is trying to use the classical machine learning algorithms using classical type of data. So this is our normal classical machine learning. Whereas if you are using classical data, at the same time you want to use some kind of machine learning algorithms which are of quantum nature, or they're quantum machine learning algorithm, then we are in the quadrant CQ. Okay, then we are having the data which is quantum, but we are trying to use the classical machine learning, so we are having QC. And then we are having completely quantum. Okay, that is, the data is also nature of quantum, and the algorithm which you are trying to use, they are also quantum, so we are having QQ. But this particular quadrant is still being used by very few people, and people are mostly trying to use this CQ or QC. Okay, mostly major of the people are trying to use this CQ, and they are working in this. So now obviously the question will come in your mind that when we are trying to shift from the classical machine learning to quantum, how can we shift, or in what way the things are getting changed? So believe me, the things, if you know the machine learning algorithm, just few things you need to change so that those algorithms can be modified for quantum infrastructure. So I'll be showing you a few examples, then probably those who are knowing those algorithms, they can see that very less modifications we are trying to do in the algorithm. So here, for all such kind of fields, you can see we can possibly try to use the quantum thing, and possibly we are trying to change that particular field in machine learning to the quantum, like the traditional machine learning algorithm, or maybe the SA or Markov chain or Monte Carlo, or maybe some kind of neural network, some kind of reinforcement learning. So those things can be modified for being operated on quantum, and possibly we are giving the name to them as a maybe quantum machine learning, or maybe the quantum annealing, or you can say like the quantum neural network, and so on. Okay, so to understand now, as I mentioned you this quadrant, so many of the people are sorry, trying to have the integration of this kind of things. And most of the people who are trying to use the quantum machine learning algorithm, and so I mentioned that they are falling in this CQ, and possibly most of the people are working in this kind of CQ and CC. So this CC is nothing but these are just quantum inspired machine learning, so they are not really using quantum this thing, they are just inspired by quantum. So some of the steps they are modifying, but really they are not being executed on the quantum infrastructure. And of course we are having the hybrid algorithms also, which is trying to make the combination of CC and CQ. Okay, so that some of the if you know, if you're having a neural network, so we are having some layers over there. So the classical layers which we are having, that get replaced by some kind of quantum layers, and we are trying to have a hybridization of those things. So I'll be showing few schematics in the upcoming slides. There you can possibly see how the things are getting different. So this algorithm is playing very important role, and possibly in every algorithm we are trying to use. So just to understand it in very simple way, I just put a simple example over here. So say for example, you have a phone book, and you are searching for a particular number, okay, without rearranging the numbers. Okay, and we are assuming that the phone book possibly like you don't want to rearrange as it is, you want to see, and now you want to, so basically it's a search problem and you want to handle it very efficiently. So the solution which is being given over here is you can magnify the amplitude of the chosen number. Okay, so here what you can do, you can select a particular region, and in that region you try to search. So that's why here that is called as amplitude selection. And now you can select the amplitude, or you can just change the amplitude, and you can do these things multiple time. So here, what is the first step? You can select the amplitude, then you can flip the amplitude of the selected item and rotate all the amplitude around the average. So just you are playing around, selecting the amplitude and moving here and there, or enlarging it, shrinking it, and just trying to do it. And this kind of thing has to be repeated until the selected item's probability of being read is greater than one half. So that is the thing, up till, or we can say till the half of this you need to do this, and possibly you will be getting the thing. So just to show this algorithm, very simple, or in the quantum way, you can show this algorithm that, first of all, you are starting with the initial state. Okay, then possibly you are initializing the superposition by applying the Hadamard transform, as I have shown you earlier. And now um, for this particular number of times, what you are trying to do, you are applying this Grover operator for searching. Okay, and of course during this, or maybe in this kind of activity, that many times when you are doing your answer, you will get the answer, and possibly you can say whether you search that particular element successfully or not, whether that element is present or not. So that is how the things are working. Okay, so this is basically a Grover operation. And if you can see the Grover operator which is being used over here, so just here I have mentioned here, this is apply the Grover operator. So now one need to understand in what way this operator is being used. So this is the schematic, and one more time I am giving a disclaimer that here I am not going into detail of the mathematics of the quantum, because it is not very easy to understand. So possibly I'll request all the participants to just quickly go through the basics of the quantum, and possibly when you again come back to the slides and try to understand, it will be easier for you to understand. So here possibly we know that we are trying to give here some state as an input, and this is being given to the Hadamard. Okay, and here there is an oracle, okay, which is trying to work again here. We are using Hadamard. So here, and we are trying to do some kind of phase shifting also. That's why I mentioned you that we are taking an amplitude and we are trying to play around the amplitude, and that is how we are repeating this root n times, O of root n times, and possibly then we'll be getting the output. And this particular operator is playing important role in efficiently searching the thing in a large, very large data set. And that is how it is, we can say that this kind of property is making it very useful um, um, for this quantum algorithms to be applicable to for the big data, or for the larger data sets which we try to use in any of the application. Yeah, so now just once this Grover operator is being used or implemented, and of course if you use some kind of simulators, they have readily available libraries, and this operator is being available over there. You don't need to really write a code for it, and possibly if you can use it in your algorithms, it is doing the job of searching. So it is just a single instruction which you can write, and it is performing the task of searching. So really you don't need to actually write the code for the algorithm which I have shown you over there. Now coming to the algorithms which we are trying to see, that how from classical they are trying to go towards quantum. So believe me, now when I'm showing you algorithm, you can see that it is so easy that the algorithms are getting modified from classical to the quantum. So in what way it is trying to modify? So if you can see this algorithm, okay, so if you forget about this second this thing, okay, so normally if you take a classical k-means algorithm, so the process is we are trying to calculate the centroid, and then we are trying to assign those samples to the closest centroid. Okay, and now the how to calculate the closest centroid. So possibly we are using some kind of distance parameters over there, and using that we are trying to find out which is closest, and we try to put that thing in those a particular cluster. So that is a normal procedure. Here only one thing we are trying to change, okay, in the existing algorithm is, whenever we try to use the this thing, find the closest centroid, we are trying to make use of the Grover search algorithm. Okay, so the algorithm which I have explained earlier, so everywhere they are trying to use the algorithm to do some kind of basic operation which is required in that machine learning, and possibly using that you can find out the closest centroid, and once you know the centroid, you can just assign the vector to the closest, you can find the closest centroid by using Grover search, and the vector can be assigned to that closest centroid. So if you can see the algorithm, just this second step is getting changed in our classical k-means algorithm, and that is how we are trying to change from the classical to the quantum k-means. So if you can see the other kinds of algorithms also, you can just change the phenomena of the algorithm with the help of the applicability of the Grover algorithm, and possibly you can modify it from the classical to quantum. Okay, and of course here now one can have a question that what is the purpose of this, or what is the benefit which we are getting um, by using this kind of approach. Believe me, here we are not using quantum computing for improving the accuracy. Okay, here ultimate goal of using quantum computing is to improve the speed up, because we know that the machine learning and deep learning algorithms, they require huge computing power, and of course that is we have seen that now when we are using some kind of deep learning algorithm or machine learning algorithm in a intensive data driven application, so it takes hours and days to train the model and to come up with the answer. So here only the thing which is being used, or possibly we can do this for the speed up only. So now obviously one can ask me, if HPC is available, why to go for quantum? So the thing is, if you are using HPC, okay, explicitly you need to assign it to multiple cores, and then they are performing the task. And of course nowadays there are some kind of mechanism available where internally this thing is being done, but still there are few some kind of problems with directly using HPC, and it is trying to give you some speed up. But really if you want a very very good speed up, then the solution is using some kind of quantum nature into it, so that you can get a very good speed up even compared to the HPC. And that's what I was just reminding you, that the last slide which sir has shown in his talk, that was very very useful, and how those people are trying to do the hybridization of quantum and HPC, so that because both the platforms are giving some kind of different this thing outcome, so they just want to integrate it, so that obviously the results or outcome will be very good. And yeah, so that's what I was mentioning, that you cannot expect that this kind of algorithm, quantum machine learning algorithm, will improve the quality of the clusters in this probable in this clustering algorithm, or the accuracy we can say. Probably it is just being used to improve the speed, that's it, and nothing else. And that's why many people now fascinated towards quantum machine learning, and they want to use quantum machine learning. But believe me, whatever accuracy you're getting in classical, same accuracy you're getting by using quantum, only the speed is getting decreased for training the model, and of course testing that model. Yeah, so similarly if you can see, now I have just put few algorithms over here, so that you can get the idea that in what way the things are getting changed. And it is not uh, a rocket science where people cannot work. Obviously you can use some simulator and you can work. only thing is just you need to know that in at what point the classical algorithm need to be modified, so that it becomes, or it will become a of the quantum nature. So those who have work in the machine learning, so easily they can switch from this to this for the speed up. So of course here in the k-means we have seen that sometime it may so happen that the centroid may lay outside the manifold in which the points are located. So now we can just modify it little bit, and we can have a approach of median, and we can calculate the median, and that median can be calculated now by using Grover. So everywhere the central point wherein we are trying to change, or we are trying to use, make it quantum by using Grover. And of course then iteratively we are calling this routine to reassign the element. So to calculate the distance from any point which is given as xi to all other points, okay, this kind of distance, earlier we were using some kind of distance calculator, as I mentioned. Now we are trying to use or replace it by using the Grover. So now if you can see here, just the algorithm change happening over here. So you can see we are having cluster and their medians, and for all xi same thing, I'm just trying to put in the pseudo fashion. And here we are trying to attach the closest center. So this closest center can be calculated by using the this thing, the just a minute. Yeah, so I was mentioning this. So here that is being replaced by the Grover search. So you can see probably here we are trying to calculate the median, we are trying to find out the closest centroid, closest cluster. So here both the things are being done. So attached to the closest center, here we are using Grover algorithm, and calculate the median of the cluster. So here also we are trying to use the Grover algorithm. So that is how the things are there. So I'll be mentioning few of the reading slides. So probably you can go and explore those things, so that you can get more insights about these algorithms. And if you want, there are many websites where the readily available code is there, and possibly you can use some of the simulating platform of the quantum, and you can probably execute those things. Yeah, so similarly now we are having the, so just here my ultimate aim is to tell you that in what way the classical machine learning algorithms are trying to modify it by using the quantum mechanism. So if you can see now, those who are already worked on this kind of algorithm, so if you can see, this is our algorithm, okay, where we are trying to find out the distance point, and then we are trying to assign it to new clusters. Okay, so this is the typical thing. Now one can ask me where exactly the quantum thing is being used. Okay, so now here we are trying to find the most distant point xi and xj in C. So at this particular step, of course you are using Grover, okay, and then you can possibly try to get, okay, because here again, on the based on the proximity or the distance which you are having, you are trying to assign it, and that distance calculation is being done with the help of Grover algorithm. Okay, so that is how the things are working. Now coming to the neural network. So if you can see over here, the classical neural networks, we already seen it, or people are using it. Of course every one of us has used it for our this thing, model development and all. So we are having input layers, we are having hidden layers, and we are having output layer. And of course here you can see this is fully connected layer. Now when I'm trying to modify it from the classical neural network to quantum neural network, so the schematic is getting changed. So possibly here I can say I am having the input layer like this, okay, and then instead of having the full connectivity with the next layer, so I can have here hidden layer, and this may be the output layer. So now I can have here from this to this to this to this, here multiple kind of you can see the things are emanating from this, and they're reaching to each of the neurons. So instead of having here direct connection, now we are trying to indirectly connect this neuron with other neuron from one layer to another layer. And possibly here we are trying to make use of the states which we have used, and accordingly those can be getting connected. So this is just the visualization to understand what is the difference between the traditional neural network and the quantum neural network. Now you can see like how we are trying to change it from the classical neural network to quantum neural network. So here, instead of using all the layers as classical layers, as I have shown you here, in the traditional, all the layers are classical neurons layer. Now here what I did, these two layers are classical neurons, but this layer is of quantum. Okay, so now here what we are trying to do, we are mixing the layers of classical and quantum component. And of course here the input nodes which we are trying to show, they are replaced by the slits through which the quantum particle can travel. Okay, now here the thing is, when we are trying to understand how quantum is working, so basically either you are using a photon and or maybe electron, and how the particles are traveling and how they are getting represented, that is the basic phenomena which is being used. So here we are trying to show that input nodes as the particle. Okay, and through the slits, maybe if you're having a narrow slits, so here for example, if you are having a narrow slit, they can reach up to this neuron and this neuron of the next layer. They cannot reach to other neuron. But if they are having a wider slit, they may reach to this neuron and up to last neuron also. So likewise the structure wise the change is there. And of course here the particles which we are trying to understand or use over there, they are some kind of unitary operations, or some kind of unitary operations are being applicable over there. And the interference pattern is drawn on a measurement device. That's why I said if there is a slit, a narrow slit, so the range in which the particle can travel may be smaller, or maybe depending on the slit size the range is lower, and that many neurons can communicate with the earlier computing quantum computing layer. And that is how the things are there. Now this interference pattern which is being used over there, so this interference pattern is replacing our traditional concept of weights. Okay, through which we are trying to have the balancing of the things, and we adjust the weights, and accordingly the things are working. So here the pattern need to be modified. So obviously we are adjusting the weight, so we are changing the weights in our traditional neural network. Here we are using interference pattern. Okay, and this pattern need to be changed. Okay, and how that pattern can be changed now. So of course here the Grover algorithm is being used. So here also the training is happening, and in a classical neural network we used to adjust the weight in the training. So here we are trying to adjust the interference pattern, but now here we are trying to use Grover algorithm, and using that the interference patterns are getting change, and that is how the algorithm is working. So obviously as I already mentioned, you may have a um, question in your mind that now if I am using quantum layer, what kind of possible good expectations I can keep from the network. So here, even though we are using the quantum layers, in terms of learning capacity, there is no difference. Okay, the learning capacity is as much as your classical networks which we are having. So that's why I say in terms of accuracy, in terms of learning, or in terms of training, or getting the efficiency, it is exactly same. We are not getting any improvement on that. Only the advantage is just a minute. Only the advantage is um the performance is getting generalized. Okay, and of course when we are having some low error tolerance, at that point only we are getting a good speed up compared to the classical computer. But of course here, for that you need to change the network. And we know that nowadays we are having so many advancement in the programming, and possibly you can create your own networks, like people are using MATLAB Simulink and all, or any other kind of simulation wherein you can just take the black boxes and you can connect each other and you can see the performance. So similar to that, also in the simulator you can have such kind of thing, but of course it is on simulator, so performance is also given on the simulator only. Actual performance you cannot compare, as you're not using the actual quantum computer over there. So now here there is some variational quantum algorithm just to show you the how the things are getting. So if say for example you are having input, and now I'm trying to um, represent that input in terms of quantum state, and from that you are trying to apply some kind of operations, and from that you're getting a feature map. So if you compare, this is like our traditional method which we are doing. And of course here in variational algorithm, the similar kind of thing is being done, as even in the previous keynote talk sir was mentioning. So here first feature map is getting calculated, and the variational model is being built on the top of that, and then you are getting some kind of patterns, or you're measuring that thing, and that is how you're getting the output. Similarly, if you're trying to use the continuous variable this thing, so the architecture can be modified in this. And this is a typical layer architecture, a single layer representation of that. Likewise, you can have multiple layers and you can get. So here I have this feature map u. Okay, so likewise you are having here multiple feature map, and you can use some kind of operations over there, and that is how the things are working. So when I'm trying to combine all these things, so if you can see over here, this is this is ultimately the feature map which you have seen, then some kind of hadamard operation, then you are using some kind of swapping, some phase estimation we are doing. So here simple, this is just a simple swap test and phase estimation which is being used inside the network, where we are trying to use this kind of mechanism, and possibly it is trying to give you. So this is for first layer, then second layer, and so on. Likewise you are having. And possibly by using this kind of mechanism you are trying to improve the speed. So similarly here, this is again the repeat until this thing which is being used over here. So here I'm not going into detail, just I'm trying to give you the gist so that you can probably explore the things and see in what way the things are changing from classical to the quantum. So by this the things are working. So up till now we have seen just how the traditional neural network is trying to change in the, or we are trying to change it in the into quantum. Now one can say that now it is fine, machine learning we have changed, the neural network have changed. So can we just change some sort of algorithms which are being used for some specific purposes like GAN and other algorithm? So obviously here we are having the quantum inspired version of GAN, and or we can say it is quantum GAN, which is again some kind of mechanism which we are trying to put. So if you see the traditional model which is being used for the GAN, of course we are having a data source. Okay, we are having some generator and we are having discriminator. So this thing we already have in our this thing, and here we are now trying to put, or of course here this noise is also there. So this is our typical thing. Now we are just trying to represent this in terms of quantum, and here the structure is getting changed like this. And here maybe here we are having the generator. Okay, we are having the discriminator over here. Okay, the data is getting sent over here, and you can see some kind of operations we are trying to perform over here, which is of quantum nature. And that is how you can possibly change your generative adversarial network to quantum. Again here, just as earlier I have mentioned, here it is trying to give you the better speed up. If you compare this with your traditional GAN, the accuracy or the capabilities of the model will be exactly same as what we are getting in the classical. So now to sum up, just to sum up this kind of this thing, that how the things are, how I can get the advantage of quantum when I'm trying to use it in the machine learning. So possibly when we are trying to use some kind of quantum mechanism, the optimization is getting improved, okay, compared to the classical this thing. The pattern recognition process which is being used in many of the networks for finding the automated features, that is getting improved. And of course the simulation and modeling is bit enhanced. And the last one is whatever data or the things which you are giving, the processing of that is getting faster. So even if this optimization is enhanced, the pattern recognition is enhanced, there is no significant change in the accuracy. Okay, of course we are getting a significant change or the improvement in the speed of the quantum. But as I mentioned now, for theoretically it sounds very very easy, that just you need to use Grover algorithm at multiple points, and you can use it to do the operation, basic operations which you want to do, and that is how you can change your classical machine learning to the quantum machine. But there are some challenges and limitations also. Of course your hardware limitation, we always have a hardware limitation. Even if you are using some simulators, they have a hardware limitations. And if you want to use more hardware, of course you need to pay a lot. The algorithm development, people are more comfortable to develop the classical algorithms than the quantum, because of the um, availability of the basic things. Of course here people are now trying to come up with the solutions. And that's why being a computer engineer or being a engineer, it is a bit difficult to understand at the first point, because possibly the people who are like a physicist, or maybe the people who are coming from the mechanics background, they can understand the basic functionality or basic working of quantum in very very easy way. But for us to understand it, it is little bit difficult. Of course we can start from the scratch, we can learn the basics, and then it is easier to understand. So most of the people who are working on the quantum, they're working in the application field, and they're trying to solve the problems using quantum infrastructure. And they really don't need to bother about what kind of hardware is being used underneath, and whether they're because they don't need to interact with the hardware when they are using simulation. But the as we are trying to see that if you are having very very large data or voluminous data, and on that we are trying to put, so the hardware support which is being given for the simulator is limited. And then in that case you need to pay. And I told you that the money which you need to invest for the hardware is very very high. Okay, and of course in the problems, like say for example, I'm working on a real time problem, like say for example disaster management. So it requires very fast decision capabilities, and I need fast processing of the data which I am getting. The system is getting feeded time to time, and I need very accurate results in no time. So there, obviously we don't mind investing money on that, and we can possibly do that. So the basic thing just I want to highlight is hardware limitation is there, algorithm deployment is there, data availability, and of course integration with classical systems. So people are more comfortable with the classical system. So if you want to integrate it with the classical, possibly there are many challenges when you start implementing it at theoretical level. We cannot see all the challenges, or we cannot face, but when once you start implementing it practically, it becomes difficult, and many people are facing the problems to integrate the classical and the quantum. So these are a few things for the quantum machine learning. Now of course I know that participants are more interested in understanding whether such kind of things are available somewhere and can we use that thing. So there are many quantum hardware which are being available. So I have just put here few of the names, and we are having IBM. So Qiskit is one of the this thing. Not open source we can say, but some kind of facilities or some kind of functionalities are made available by IBM, and possibly you can use that simulator, this thing. Then Google has now come up with TensorFlow Quantum, and that you can probably use for quantum machine learning. So you can try it. Maybe as I was mentioning, there are some inbuilt plugins, or there are some functionalities readily available, black box functionalities which you can probably use and perform. Then Microsoft is having Q hash, AWS is coming with the bracket, and so on. And Nvidia is coming with Q quantum, and of course it is trying to have a blend of HPC and quantum over there. Then we are having Xanadu, and this is working on the photonic, and then we are having the atom computing. So this is atom based environment where people can use it. But most of the time this infrastructure is a very costly affair, and that's why possibly people can. So that's why I said IBM is providing this thing, and you can use it, and maybe you can pay per use policies there. So as per your need you can use and you can pay. Similar thing is with bracket also, and possibly you can use it. Coming to the people or the players who are providing us the quantum as a service. So as I said, IBM is one of the big player and the major player in this market. Then we are having some D-Wave system which is coming up with the solution called as Leap or Ocean. Then we are having the quantum playground, or I just mentioned Tensor Quantum. Then Microsoft, Amazon, they're coming up with their own this thing. And likewise there are many quantum computing as a services available nowadays, which you can probably use to execute your programs on that particular simulated environment using this computing as a quantum computing as a service. Yeah, so few of the things. So coming to the last part of my talk, here I am just putting here in what way quantum computing is helping us in the research. So believe me, whichever field you are seeing, everywhere we can make use of quantum. So technology wise, if you say we are having quantum sensors, so somebody who are working in semiconductors or maybe some sensors and all, possibly they can obviously work on quantum sensors. And believe me, in India, even though the premier institutes like IITs and CDAC and all, they are trying to work. So still they are taking the basic parts from the other countries. So recently we visited ICER Pune, and we visited few other laboratories to see the quantum setup. Like we visited some of the institute in Delhi, and they have their own setups, but those setups are just for doing a preliminary experimentation. And still the people are trying to come up with the solution, and that's why here there are plenty of the opportunity to do research in this kind of field, those who are from the electronics or such kind of background. Then we are having quantum networks. So if you want to share or send quantum data from one particular part to another part. So still it is not possible. And so that's why I was mentioning that when we visited some of the laboratories in Pune, so they are trying to build up, they have built up one mechanism or the quantum infrastructure wherein they just try to have the communication, which is I think up to some hundreds kilometers they could able to do, not beyond that. So people are trying to build those things. And of course I told you quantum hardware. So in India, we do not have a quantum hardware. And the semiconductor devices or the photons and all those things, people are even importing those for their experimentation. And of course quantum software, quantum AI, the quantum machine learning, lot many opportunities are there for the researchers to contribute. The application development on quantum, the various solutions for the current need, the communication as I was mentioning. And when we are using photonic and all, we know that the noise and the attenuation is the biggest problem. And of course people are trying to work on that. The quantum security, the quantum blockchain, so lot many things are there. And of course those who are from the security field, we know that quantum can do the operations faster. And like if you take the RSA algorithm, which is again the security of the RSA algorithm is based on the factorizing of the numbers. And we know that today the system cannot do that. The classical computers cannot do that. But if you are having a quantum computers, then easily that security can be broken. And if the this kind of implementation or the quantum computers are getting successful to get made, then eventually the complete phenomenon of security will be changed. And the algorithms which we are relying on nowadays, like AES, DES, RSA and all those things, they cannot work because of this kind of nature of the system. And then we need to come up with some kind of different algorithm. That's why in this field also quantum is playing very very important role. And along with this, if you see the disciplines where people can work, so of course we are having the linear algebra, mathematics and statistics, physics, because these are the base superconducting physics, as I was mentioning, photonic and quantum optics, the algorithmic development of in the field of machine learning, deep learning, AI, in what way the classical algorithms can be modified for the quantum. And of course I mentioned Fourier transform and Hadamard, all those things are very very, they are playing very important role in the basics of the quantum. And probably if you give some solutions on that or in that particular field, that will be helpful in the quantum. Then networking and system engineering is also some of the discipline. Now of course here, what are all different emerging trends which we are having? So one of the trend which I just took for the today's talk, so that is quantum machine learning. Now you can see there are a lot many articles coming in, research articles coming in, which are trying to use quantum in the natural language processing. And now you can see we are using heavily the LLMs and all. And just imagine if quantum is being used in LLMs and over there, what kind of speed you can get and how the things are getting changed in the future. Of course, quantum key distribution is one of the very important thing, and quantum cryptography, as I mentioned. So the key generated, because we know that the security of whole or the communications security is dependent on what kind of key you are using and how that key is getting distributed and all. So basically people are trying to come up with the distribution mechanism which is using the quantum. So recently we have come up with the laboratory in our organization, that is quantum laboratory. And of course we could not have a quantum computer, we cannot take, as it is very very costly, but we have taken the quantum key distribution kit, and using some kind of quantum phenomena, it is generating the key. And if you see the key which is being generated using those kind of infrastructure, that is having truly randomized nature, and possibly you can make use of that key which is getting generated through that quantum this thing. If you're using that, your algorithms or your communication will never get compromised, because it is not at all possible to launch any sort of attack on those kind of key. So people are trying to use it. So as the engineering institute, we have taken it at the application layer and application level, and we try to um, um, how the infrastructure, the hardware infrastructure which can possibly generate the quantum key, and which can be used in numerous applications to make those application secure. So if anybody wants to visit and see, you are welcome to see our laboratory and the function of the quantum key distribution kit which we are having. And of course it is trying to distribute the key or send the key over 22 kilometers. So we are having 22 kilometers this thing, fiber optics cable, and through that, from one end to another end, you can see how the quantum key distribution or key generation is happening and the key distribution is happening. So these are a few things which are very fascinating and people are working. And of course quantum cryptography, I told you, the whole communication, the security which is underlying on that, everything will be changed in future as the quantum computers are coming in picture. But still it is in infancy stage, and people are trying to work on. So lots of people are doing research on quantum cryptography, and how the things are getting changed with the help of quantum, that people are trying to find. And of course the general applications which we are having, like finance, healthcare, then of course in some kind of advanced research and space communication and all those things, there also we can have this kind of technology. And these are the emerging trends, and lot many things can be done over here. So those who want to pursue the career or research career in this field, this is upcoming inspiring field. But of course you need to understand the basic, lots of hard work is required, because you cannot just take the quantum as a black box. You need to understand the basic, and then probably you can come up with the novel ideas and the contributions to make this field more useful or usable in various things. Yeah, so as I mentioned, now there are applications, and there are emerging trends. So many applications are there where people can use. But so just to name a few, we can use quantum computing to solve the optimization problem, because these are of complex nature and it requires lots of computing. So there we can possibly use quantum computing. Also wherever we are having large data set, or we are having intensive data and you want to work on that, so you can possibly use some kind of evolutionary systems where you need a exponential speed up. There you can possibly use such kind of mechanism. But of course at the same time we have the other side of the coin, and we have lot many challenges when it comes to usage of quantum computing. So the quantum hardware not yet large scale and stable. So I mentioned you, still people are trying to build the quantum computers, and they are not like coming up with the complete setup, and lots of things they are taking from the other countries. So still it is in growing field, or people are trying to work. The quantum software needs lot of work, because the simulator which you are building, or the application which you are building, that should understand how the things are working at the underneath, and accordingly the things need to be done. So that is again one of the challenge. And no software framework exists for quantum algorithm development and quantum machine learning. Okay, so there is no exclusive algorithms or the software which is being used. So you need to have the combination of classical and quantum, and then possibly you can come up with the algorithmic development for maybe the quantum machine learning. Okay, so of course people are working, and since a decade people are working on it and coming up with different solutions. Okay, so these are few applications and challenges. So just to end my talk, I would like to end it with the quote by Bohr, and it says that if the quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So that's why I said, talking about quantum computing is easy, but sitting it and implementing it, doing the experimentation is very difficult. So it is my request to all the participants to try to download the open source or freely available softwares, and try to see there are so many small scripts available online over the internet, and you can just try to execute and see how, what kind of performance it is giving, how it is working. So just to share with you that, like, we are having that this thing, quantum key generation kit, but the key which you are getting is very large, and now I just want to use that key in some of the software, and the software should be capable to take that much of thing in the structure which they are using. So likewise the things are there. So when it is coming to such kind of things, the softwares, the framework which they are using, that should be probably modified, so that possibly the capabilities of the quantum computing can be absorbed and people can start working on it. So just to end this, even though quantum computing is like, it is emerging area and lots of people are getting fascinated by this field, but for the newcomer, the thing is, first you try to learn the basics of this, understand it, and then probably as per the application in which you want to work, you try to explore, or you try to see in what way I can modify, or in what way I can contribute, so that the framework and everything can be capable to use those kind of things, and possibly you can run your application which is being developed for the application, and you can get some sort of results wherein you can get a better speed up or exponential speed up. Okay, yeah, so these are few readings, possibly you can go through it. I'll be passing this presentation to organizers, you can possibly go through it, and there are a few more links which I'll be sharing separately. So those are the web resources where the participants can go through, and they can learn more detail about the quantum computing. So I hope I could just give you the gist of the quantum machine learning, because I saw there is one more session which will be um, uh, uh, in your schedule. There will be one more session on quantum machine learning. So probably if the professor or maybe the speaker will be taking some kind of hands-on or showing some demonstration, you will get the actual you get to see that how exactly the quantum machine learnings are getting used. But readily some programs are available online, you can download and you can try to implement, or you can try to run it on IBM Qiskit, and you can see the performance of that. Okay, so with this I come to end my talk. If you are having any question, I'm here to answer. Thank you.
Thank you, ma'am. Participants, if you have any query, you can put it in chat box or you can unmute yourself and ask.
Shaila madam, there are some two,
There are
three queries.
questions in chat box. Yes. Ma'am, there is question, what kind of problems can be solved using quantum computing simulators?
Yeah. So as I mentioned, any problem which you can solve using classical computing can be solved using quantum computing. But then we need to first understand, uh, if you really need a very large speed up, exponential speed up, then only go for the quantum. Otherwise, you will end up in investing lots of power and lots of infrastructure. So that's why I was mentioning the like all the things I have mentioned in the classical, and how we can modify that into quantum. So lot many things can be done, but of course we need to see wherever you need a speed up and faster, very fast operations to be performed, then at that time you can use probably quantum computing.
We have another question from Ankush Patil sir. Do we use Grover diffusion?
Grover diffusion is being used at multiple time. I have not highlighted that, but it is being used in many of the algorithms.
Okay, we have one more question. What are research areas in quantum computing from Dr. Nitin Chopde?
Yeah, so I think the last 2 3 slides I have already mentioned what are all research areas. So if you are from the cryptography field, this is one of the area wherein you can contribute, and lots of research is needed in this field, and possibly you can come out even. And believe me, if you just start with simple, like we are doing some sort of basic operations in AES and DS, and if you can replace those operations, they are giving you better and better speedy operation, because we know that AES and DS, their AES is a bit slower algorithms when you're having a large data to be encrypted and all. So there possibly you can do lot much of contribution, and I told you in machine learning and all, there also you can do probably research if you are working at the application side. And if your core this thing like hardware engineer, or maybe the people from electronics background, the communication background, they have plenty of the opportunities wherein they can do the research. Like I told you that there are lot many problems with the attenuations and all those things if you're not doing the setting properly. I just urge everyone just to try to see some setup of quantum, and you won't believe, it is a big room where the complete thing is blackened, okay, so that there should not be any noise or attenuations and all those things because of the sunlight and all, depending on what kind of mechanism is being used for generation of that bits, quantum bits and all. So lots many things are can be done at that particular point. Also in communication also, you can do some kind of contributions by putting some kind of efforts towards the error free communication. And yeah, that is one of the again very important and the upcoming research field in quantum. The when we are transferring the quantum key, for example, so depending on the network or the communication channels, this thing like sometime the channel may be corrupt, or maybe some kind of noise is getting added. So in that way the whole purpose of that thing is failed. So people can start, or people can work on that. So many people are working in that field, and you can see lot many every day. You can get lot many papers on this, and of course you can start working on it.
One more question is there. Kindly suggest proper application of quantum computing.
Yeah, so I think I have already answered for this.
Can we co-relevant with cloud's data security with quantum computing?
I really didn't get this question. What do you mean by
Yeah.
that, co-relevant with cloud data security with
Uh,
quantum computing?
Sachin sir, can you please unmute and ask your question?
Yes, madam. My question is there. If we require the increase the cloud data security, can it be possible to implement the quantum computing with the
Sir, these things are totally different. Cloud data security is very different, and quantum computing
no,
is
but
different. You
but
can use quantum
we are
computing for
increasing the algorithm
any
for the
purpose.
no, we are increasing the algorithm for the enhancing the cloud data security. So it is possible that some machine learning or the some quantum computing can be helping
Yeah,
that.
so if you are saying, for example, the application is cloud data security, and the users are putting some data on cloud, and cloud is implementing some sort of security
Exactly.
algorithms over there. So you mean to say that whether quantum computing is useful over there or not, right? If I correctly took your question.
Yes, yes, definitely, ma'am. Yes.
So in that case also, like when you're storing the data, you're using some kind of security mechanism. So that's why I'm saying, if you're having the quantum computers build, we are having the other side, negative side of it. It is very very easy to break that security system. Okay, and of course, the next thing is, then you can make use of quantum system to make your algorithm so secure, or you can change or come up with the new version of those algorithms, so that it is giving you the better security. And as it is built on the top of quantum, obviously the security cannot be broken by any of the computing system.
Okay, madam. Got it. Got it.
Yeah.
Participants, any question is there? I think all questions are answered.
Okay, yeah.
Um,
So thank you all of you for patient listening. And I know that the very first session I put, and lot many things I have added, but that's why I'm saying, like, a few sessions are coming up in your schedule, where you will be also learning the basics of quantum computing. But you can go through the resources which I'll be sharing, and possibly you can learn by yourself that the basics, and then probably you can understand in